Today I am going to discuss the merchant circle theory. Why this merchant circle theory is basically used? We know that during the cutting operation, various forces are generated during the turning of the material. These forces we need to represent with the ease, and therefore this merchant circle theory concept comes into existence. What are the importance of studying this merchant circle theory? We know that people are working in the research area, so with the help of this merchant circle theory, we can represent the forces which are generated during the turning operation in the circular format, and we are able to derive the equations for that, and we are able to extract the information from the turning process, and we get some numerical value from these derivations. So, I'll first draw the figure of single point, a simple mechanism of metal cutting. This is basically the workpiece. Here I am using a single point cutting tool. The chips are removing along the shear plane. These are basically the chips. I am assuming this point because this point plays an important role while discussing this merchant circle theory. So along with that, I am just taking one axis, horizontal axis. So this angle is basically angle phi. So before entering, I would like to tell that before entering into the merchant circle theory, we need to presume some assumptions. The assumptions are: the chip thickness is constant, shear force is acting upward, cutting velocity of the tool is constant, and there is no built-up edge. No built-up edge. So these are the various important assumptions while discussing the merchant circle theory, right? So I am assuming this point as A, where tool is coming into contact with the workpiece, and along this the tool is moving in the horizontal direction with a velocity of cutting velocity of Vc. So Vc is nothing but the cutting velocity. This direction we can this is basically the T1. Here we call T1 as uncut chip thickness. This is basically the dimension of the cut chip thickness denoted by T2. So T2 denotes the cut chip thickness. These parameters plays a very important role by determining the various forces which are generated during the cutting operations. The ratio of these is called R, T1 upon T2, which is nothing but the chip thickness ratio or cutting ratio. The reciprocal of this is called chip reduction coefficient. So we have denoted is the cutting velocity, which is the tool is moving along the horizontal direction. The feed is giving around the horizontal direction. Along with this, the forces are generated. This forces is nothing but the cutting force, which is called as the cutting force, which is in the horizontal direction. The perpendicular to this cutting force, there will be the thrust force at this particular point, denoted by Ft. Along with this shear wave, this is basically the shear plane, along which the material will be removed, and the force acting along this direction is denoted by Fs, that is shear force. So I am presuming one vertical axis to determine the angle this force is making along with the vertical axis. This is denoted by alpha, which is very important in merchant circle theory. Alpha is nothing but the rectangle. So phi, with which the material will be removed from the surface of work, is denoted by the angle phi, which is the shear angle. So now we have established one figure to calculate. So we can say along with this tool and the chip, there will be some friction. So this is represented by the frictional force. There will be some kind of force that will assign in between the chips and the tool. So denoted by frictional force. Along with that, there will be the chips are moving from the surface of shank surface of the tool with some velocity, which is denoted by frictional velocity. So we have seen along with the shear plane, the material is removed. So here we'll find one shear velocity. So this will denote Vs is nothing but the shear velocity. Vf denote the friction velocity. Our main motto is to determine Fc, Ft, Fs, Vc, Vs, Vf. So how we are going to determine it? So we'll presume we are presuming that. So in the simplest way, people usually find this very difficult. How to represent these forces? How to determine it? So in the simplest way, we will try to study so that, see, I am assuming here one point, that is point A. Initially I focus on this point, that is point A. From that we are able to see this is the horizontal directions. So this point is again plays an important role. I am calling it point as a B. So here point B I am calculating. So I am representing the point B. From point B we will draw one perpendicular on FC. This angle is 90 degree. So I am calculating here. This angle is point. You can assume that is point C. This angle is 90 degree. So the angle between Fs and Fc will be phi. So we will simply represent here phi. That is the shear angle. Along with that, we will take this, we will extend it to simply understand the things. How it is very simple to derive the equations. There is no need to worry for the students how to calculate this. So this is basically I am pasting only the replica of what we have discussed, and in the calculation format we are discussing it. So this angle is basically here we are going to mention this FF and VF, right? So this angle is alpha, that is the rectangle. So from this it is making angle 90 degree with this. So this angle is the phi. So this angle is 90 minus phi. This angle is 90 minus. So it is very important to understand which are the angles which are present in the what are the angles which are present in the diagram. So once we are able to determine the angles, so we can easily calculate the various forces generated during the turning process, right? Now this angle T2, so this is basically perpendicular. I am representing this T2. This is basically T1. I am just putting the replica. What we have discussed, I am putting in the triangular format so that we can easily calculate it. So from here we can draw one perpendicular. On this. This is basically 90 degree. So we can so assuming that we can so it looks like a perpendicular now. So it should be like here, that is 90 degree. So we can give this A, B, C, so we can give it point D. So this angle is basically the length of this BD is FT, T2. So we are giving it, right? So now we have different formats and we can easily calculate the T2 and T1. So how we are going to calculate T1 and T2 once we know? So simple geometric equations we are using it. For example, from this figure, from triangle ACB, sine of phi is equal to opposite upon hypotenuse, right? So T1 upon AB, right? From this figure, from triangle B D A, we can calculate sine of what this angle will be 90 minus this angle will be 90 minus 5 plus alpha. Sine of 90 minus 5 plus alpha is equal to opposite upon hypotenuse. So this is basically the hypotenuse. So sine 90 minus 5 plus alpha equals to T2 upon AB. So from here we can calculate T1 is equal to AB sine of 5, and from here we can calculate T2 is equal to AB sine of 90 minus 5 plus alpha. So we know that there is one relation between T1 and T2 and R, that is R is nothing but the cutting ratio. We will simply take this R and T1 divided by T2. The main motto behind this, we need to find out the very important angle, that is the shear angle phi. So we are proceeding towards how to calculate the shear angle. So simply I am substituting this value T1 equal to AB sine of phi divided by AB sine of 90 minus phi plus alpha, right? So AB get cancelled here. So this we can represent as it is, like sine of phi divided by sine of, this equation can be represented by 90 minus phi minus alpha, right? So here we can represent sine of phi divided by sine of this will be become sine 90 minus theta will become cos theta, right? So theta means cos phi minus alpha, right? So we got one relation, that is R. So what we will do, I am taking here, I will just explode this equation, sine phi divided by cos A minus B. This is A and this is B. So if we know the simple geometric relations, so we can easily explore this equation. So cos A minus B will be cos A into cos B plus sine A into sine of B, right? So once we got this equation, simply what we will do in the next step, so to achieve the equation of phi, to determine the shear angles, we are processing towards the we are calculating some equations. So I am simply dividing with the help of cos phi, right? So cos phi I am dividing in the numerator, divided by cos phi. Similarly, I am dividing this whole equation cos of phi into cos alpha plus sine of phi into sine of alpha divided by cos of phi, right? So we'll again, I am taking this side, these equations I am taking. So R is equal to, we get tan phi divided by, see, if you are solving this equation, solving the denominator, what we'll get? We'll get cos phi will get cancelled, so we'll get cos of alpha, right? Sin phi divided by, so tan of phi into sine of alpha, right? So I hope it is clear till now. Then we'll take this on the right side. So R cos of alpha plus R tan phi into sine of alpha is equal to tan phi, right? So what I am taking on this right side, R cos of alpha is equal to tan phi minus R tan phi into sine of alpha, right? So we will take it out, tan phi common, means we will take tan phi common from the right side, so we will get 1 minus R sine of alpha, right, is equal to R cos of alpha. So tan phi will be equal to R cos of alpha divided by 1 minus R sine of alpha. So this equation actually very important from the gate point of view as well as the examination point of view. So this will definitely will ask in the examinations how to derive the angle for the shear angle. So with this calculation we can easily determine the tan phi. Once we know r, this angle will be given, r means rack angle will be given. So and the chip thickness of the chip before cutting and after cutting will be given. So we can easily determine the phi shear angle from this equation. I hope it is clear now. Now next step is I have to determine the various forces which are acting, which are generated during the turning process. So I am just removing it from here. So this is very important question will definitely ask from this mechanics of metal cutting, derive merchant circle theory and how to determine the various forces. Simply what I did, I just represented the replica of the figure in the triangular format, and with the help of some geometrical relations I derived the equations, right? So another thing is how to represent these various forces during the turning processes. So simply merchant circle theory, how it plays an important role. So we will simply take the circle. So this point is played an important role. I initially focus on this point. So here I am just doing this point is A, assuming there is a tool will be here, going from here, right? So this is the contact surface of the tool with the workpiece, right? So tool is moving in the horizontal direction with some cutting forces. So this cutting force FC I am representing here. So whenever you want to represent in merchant circle, my suggestion is you draw the figure just below your main figure, right? So you will be easily understood all these things. So this is FC I am representing. This is basically FC, that is cutting force. So we know that perpendicular to this cutting force there will be FT. So we will represent this FT here, right? So this is basically FT. So FC and FT, the resultant will be R, right? So this R is also plays an important role. So a simple figure we draw, like in the horizontal direction there will be FC, in the vertical direction perpendicular to cutting force there will be FT. Now this R we have to represent this shear force. As you can see from A there will be the shear force going upwards. So simply just copy as it is, right? So I am taking this is Fs, that is shear force. So there will be the normal to the shear force, right? So which was normal? This normal I can draw from here. So this will make angle 90 degree with this Fs. So this is basically normal to shear force. So this angle between Fs and Fc will be phi, right? So this is phi. Very simple thing. So now we have to represent this thing is remained Vf and Ff. So friction force going upward. So I am representing here in the downward direction. So this is Ff. So perpendicular to this will be the normal. So this will be the N. This angle is beta. Generally denoted as beta, means friction angle. So beta Ff, and this angle we need to calculate x. So I told you just draw in below the main figure. So we will be able to understand from point A there will be angle alpha. So I am simply representing here the angle alpha, right? So in this direction, so I am preparing. So this angle will be alpha, right? So this is beta. Sorry, this is not 90 degree. This is 90 degree. So this is beta. This is 90 degree. So this angle will be 90 minus beta, right? So from this, see every point it will make an angle of 90 degree. So you need to assume that every point, see at this point it is making an angle 90 degree. So from this we can easily calculate x plus 90 minus beta plus this alpha, right? This alpha is equal to how much? 90 degree. Right, this angle is 90 degree. So this 90 degree cancel. So x is equal to beta minus alpha. So we know this x. Now what we will do, once we know the x, we will assume 3 triangles, right? So I am assuming first triangle I will take this FC and FT. The main focus of this merger circle theory is to calculate the various forces generated during the turning operation. So here on this right side I am taking, so this is FC, I am presuming that this is FC, right? And this point is I am taking A, this point is B, here I am taking this point, it is C. So this we know this is FC, right? This is FC, this length is FT, and this angle is 90 degree. So this angle is, we have calculated. See, simply we have to extract the figures, triangles from here in merchant circle theory, and we need to apply the geometrical equations, right? So this is actually beta minus alpha x, right? So how we will calculate? Sin beta minus alpha is equal to, what is opposite upon hypotenuse? This is r, this is basically r, right? So simply I am extracting the figure from here, I am putting here to calculate the thing. So what will it will be? Opposite upon hypotenuse. Ft upon hypotenuse is what? Resultant. So from this thing, due to the less space, I am not going in representing again. So from this we will get Ft, right? Again, I am taking, this is the first figure I have taken. Now the second figure I am taking. Second figure is what? This Fs and Fn, right? So this will be like this. Simply I am copying it, right? So there is no need to worry how these figures will come. So this is Fs, this is 90 degree, and this is Fn, right? So I can give it triangle LMN. Okay, this is again R resultant. So this angle is how much? See, this is x and this is phi. So phi plus x, and x is what? Beta minus alpha. So I am simply taking what? Sin of sin of phi plus beta minus alpha is equal to opposite, means Fn upon hypotenuse r, right? Again, from this equation we can calculate this Fn, right? We can easily get normal force to shear force, right? Then we can get cos of, this is again the same relation, phi plus beta minus alpha. What will you get? Adjacent upon hypotenuse, right? So Fs upon r. So from this equation we will get Fs, right? From here we will get Fn. From here we will get Ft. So now which forces remain? Ff, frictional forces remain, right? So we will take this figure. Again I will represent this. Simply I am copying it, right? There is no change in this thing. I am copying the figure as it is. So this is 90 degree. This angle is beta, and this angle is 90 minus beta, right? So this angle is I am taking O, P, Q. Anything you can take. So again this angle is resultant, this is Fm, and this is normal. Again what we will do? We will take sin of 90 minus beta is equal to opposite, means this normal upon hypotenuse. Hypotenuse is what? Resultant, right? So from here we will get this normal force. Okay. So cos of 90 minus beta, what is this? Adjacent upon hypotenuse, right? So from here we will get Fm, right? So all the forces we can able to see, we can derive from this equation. So here unknown is R. R we can calculate from this. This is Pythagoras theorem only. So we can easily implicate the value of R. R is equal to under root of this Ft square plus x square, right? So similarly we can apply the Pythagoras theorem in all the triangles, and with this we are able to calculate the various forces which are generated during the turning process. Now only one point is remained, that is the velocities, the cutting velocity, shear velocity, frictional velocity. There is one simple rule is there. See, I have already represented. So I hope it is clear now. I will just clear it. Okay, to determine. So I will just remove all these things. So the very important thing is how we are going to represent this VC, how we are going to calculate this VC, VS and VF, that is cutting velocity, shear velocity and VF. So frictional velocity. So I am simply representing, I am using it. So this is basically VC, right? This force I am representing VC, right? This is basically Vs, right? This is Vs and this is Vf. So triangle. With the help of this triangle, we will easily calculate this. Now, how we are going to calculate this? See, the very important thing is, I told you in the earlier also, this diagram you need to learn this diagram, you need to understand this diagram, then only you can calculate this merchant circle, you can calculate this cutting velocity and all, right? So, the angle between VC and VS is what here? VC, this VC and VS is what? Phi. So, this angle is phi, right? Angle between VF and VC is, this angle is VF, right? This angle is VF and VC. This alpha, right? Alpha, this is what? We have calculated 90 minus phi, right? So this angle is, what is this angle? 90 minus pi plus phi and then alpha. 90 minus phi, right? Plus phi plus alpha, right? So what we will get here? Simply 90 plus alpha, right? 90 plus alpha. Here we will get 90 plus alpha. So this angle also we came to know. So this is what we are doing faint. Now the angle between VF and VS, right? So VF and where is VS? This one is, this angle will be VF and VS. 90 minus, here I will write 90 minus phi plus alpha. So here we will apply the sine law, right? So all the angles we came to know, angle between VS and VC, VF and VC and VF and VS. So we will apply sine law, apply sine law. Sine law. So what sine law says? Sine law says the length of any triangular any side, that is VF, is equal to, means is divided by the opposite of that angle, sine of opposite of that angle, that is sine of phi, right? Here also VS, the length of this side is divided by sine of 90 plus alpha, right? Here VF we calculated, VS we calculated, VC is denoted by sine of 90 minus phi plus alpha. So usually phi and alpha will be given in the numerical equations, so we can easily calculate the cutting velocity, shear velocity and friction velocity. So we discussed today, I am concluding here, I am summarizing all these things. What we have done, we have represent all the forces generated during the cutting operation in one single mechanics of metal cutting figure. Then we have represented this figure to calculate the various parameters, like various angle we have calculated, and shear angle we have calculated. We have derived the equation for the shear angle. Then we have come to this merchant circle theory, where we have represent all the forces in the merchant circle, and with the help of that, how we have derived the equation for each thing, and finally at the end we are able to calculate the various velocities with which the tool is moving, my chip is removing. This we have calculated with the help of this sine law. So I hope this all the lecture you understood in a very simpler way, and if you have any question, you can raise this question. So thank you so much.